So we're going to start off this week looking at section 7.2, which is on inverse trig. So I want to start out just by looking at two functions that are inverses, but not trig. Okay, just something from like algebra 1. So let's say you had this. Y equals x squared. That's a parabola, if you were to draw it, right? It's like a U shape. Well, the way you get the inverse of that is, well, actually, I'll tell you that in a second. But there's something you do to get the inverse. But before I do it, does anybody know what function is the opposite of squaring? Yep.
Square root.
Square rooting. So squaring and square rooting are what we call inverse functions. They're not trig, but they are an example of inverse functions. The way you get an inverse function is you take the x and the y and you switch them. So if I go like this, inverse is literally just take the x and the y and have them switch places. And you might be like, well, wait, that doesn't give you a square root function, but let's do that and then watch what happens. So there's your inverse. And now, how would you get y by itself here? Just like it is on this side. Yep.
Take the square root of both sides.
You'd have to take the square root of both sides. So when you take the square root of the left and the right, you get square root of x on the left, and you get y on the right. So this and that are inverse functions, exactly like you guys just said, squaring and square rooting. Okay, let's try them and see what they look like. Okay, so I'm going to put one of them in y1. I'm going to put the other one in y2. All right, so I'm going to do zoom 6 just to kind of reset that. And let's do x squared and square root of x. I also only want to focus on quadrant 1. I don't want to look at quadrants 2, 3, and 4. So what I'll do is I'll set the window so all we're going to see is quadrant 1. And let's hit graph. Okay, so there's your x squared. That's your parabola. And there's your square root. And if you look at them, there's a kind of symmetry there. Does anybody think they see like a line that you could draw on that graph? And if you folded it over that line, the blue one and the red one they'd land right on top of each other. It's not over the x or the y axis. Because if you like flip the blue one over the y axis, it would end up over here. So it's not that. Yeah?
Why do that?
Yeah. Yep. If you draw in the line y equals x, which is exactly what we just did to get the inverse, we changed the x and the y. We set y equal to x, and x turned into y. Watch what this looks like. And I'm also going to make it kind of a thinner line so it doesn't take up as much space. Okay, so now look at that. If you could fold that right on that black line, the blue one would land exactly on top of the red one. And that always happens when you have two inverse functions. They're mirror images of each other when you draw them over the line y equals x. And that's just for squaring and square rooting, but that's true for any two inverse functions. And we're going to focus on inverse trig. So as I just mentioned to you, inverse functions are mirror images or reflections of each other over the line y equals x. But that's the whole key with an inverse function. If you have any function at all, and you want to turn it into its inverse, just take the x and the y and switch them, and you just created the inverse. So here's a typical trig function we would have seen over the past couple weeks. Is y equals sine x. If I want to turn that into its inverse, just like I did right there, anybody think they could tell me what I would put on the other side? Yep.
X equals sine y.
Yep. X equals sine of y. Now, the same problem we have here is the same issue we had right here. Once you switch the x and the y, you need to get the y back by itself again. Well, here you do that by taking a square root, because square root undoes squaring. Here, you need to undo taking the sign. So we have to get rid of this sign, so y is by itself again. And you can't get rid of sign by dividing by sign, because first of all, there's no multiplication here. The parentheses are just indicating whatever number you put here is being plugged into that function. So parentheses don't always indicate multiplication, and they don't here. So we're going to talk about what function gets rid of sign, and it's called inverse sign. And I'm going to show you how to write that in a minute.
Isn't the inverse sign just sine -1?
That's the symbol for it. Yep. And I think I'll mention that. Well, at some point I write that down. Now, not every single function has an inverse, because for something to have an inverse, it has to pass a certain test. The test that it has to pass is called the horizontal line test. Okay, so you might have heard of the vertical line test. Vertical line test is used to determine if what you're looking at is a function. Horizontal line test is used to figure out if the inverse of what you're looking at is a function. And that's what we want. We want the inverse to be a function. Because in math, the nice thing about functions is, if you have a formula that's a function, it has one answer when you plug a number into it. If you use something in math that's not a function, and you plug something into it, you can get more than one answer. We don't want to get more than one answer. So we want to make sure whatever we study, it's a function. So let's think about sine. There's the graph of sine. Now, it passes the vertical line test. So we know that sine is a function. Meaning if you plug a number into sine, you will get only one number back. But now I want to think about inverse sine. And up above it says for a function to have an inverse, it has to pass the horizontal line test. That means if you draw a horizontal line, it only hits your graph once. If I put a horizontal line in there, will it only hit my graph one time? What do you think, Laura? No, it's gonna hit it. It's gonna hit it more than one time. So what that means is the graph of sine fails the horizontal line test, which means that the inverse of sine would not be a function. That's a problem. We need the inverse of sine to be a function. Otherwise, we can't get one answer to the problem. So we're going to figure out how to get around that. All right. So we need to make this function pass the horizontal line test somehow. It can't fail. Yep.
Didn't you say sine was a function?
Regular sine is a function, but its inverse, if we consider this picture right here, is not.
So that picture right there is representative of the inverse? Or
This is regular sine.
So if a function only has one answer, would that not be a function? You can still crossing the line multiple times.
So for a function to have an inverse, it has to pass the horizontal line test. This function fails the horizontal line test, which means it does not have an inverse. Right? An example of a function that does pass the horizontal line test, just think of something simple like a line like that. That line passes the horizontal line test, which means the inverse of this line would be a function. This graph fails the horizontal line test, which means the inverse of it is not a function. And that's a problem. Were you going to say something?
Yeah, we should just limit the period.
Yeah, what we're going to do is instead of looking at the entire graph of sine, we're only going to look at a small section. We're going to try to find a section that does pass the horizontal line test. Each one of these tick marks represents 90 degrees. So it's like 0, 90, 180, 270, and then 360 is a full cycle. Let's try it right there. Okay, that's about 0, 90, that's 0 to 180. That window that I keep sliding back and forth, that's a 180 degree wide rectangle. Okay, that's how wide the width is. If I set it from 0 to 180, does that section pass the horizontal line test? No. So then we don't want to look at the section from 0 to 180. Let's try a section about like that. That's from the first tick mark on the left to the first tick mark on the right. Now, if we take that line and drag it up and down, forgetting anything that's not in the window you can't see. So forget about what's to the left and the right. Just what you can see. Does that section of the graph pass the horizontal line test? Yes. Then that means that section of the graph has an inverse. So that's how we're going to get around. We're only going to look at that section. What we have to know, though, is what that section is. I told you each tick mark represented 90. So anybody think they know what the left edge and the right edge of that screen is? Yeah?
Negative 90 to 90?
Yeah, negative 90 to 90. So when we talk about the inverse of this picture, which is called inverse sine, we're only going to be looking for answers between negative 90 and 90. And by doing that, we're guaranteed everybody will get the same answer. If we decided to look at a section like that, the problem is, if I ask you a question and you consider answers in this section, some of you may get this one, some of you may get that one. You could have different answers, and we don't want different answers. We need a section that passes the test, and that's the section, negative 90 to 90. It's not the only section. You could slide this to different spots, and you could definitely find another area that passes the horizontal line test. Like right about there. That's 90 to 270. It's not that it would be wrong to use that section. It's just usually everybody and calculators use the section from negative 90 to 90. It's the section that's always used. All right. So we saw that we had a problem because sine fails the horizontal line test. And the solution to that problem is we're going to restrict the domain of sine. We're going to forget about everything that's not negative 90 to 90. And that's how inverse sine is done. That's how they do it. And you will see radians quite a bit. So when we're dealing with sine, the domain is negative pi over 2 to pi over 2. So that's how far left and right the box goes. I want to look how far up and down it goes. We didn't really look at that. How high and low. So if I put that box back at negative 90 to 90, and you might remember this anyway. What's the highest and the lowest that it goes in that box? Yeah? 1 to negative 1. 1 to negative 1. Yes. So let's write that down. So here the domain is negative 90 to 90, and the range is negative 1 to 1. And that's describing what's in that box. And that box is the original sine. So this is sine and it's the original one. So now, I want to figure out what the domain and range of the inverse would be. Well, we know the inverse is going to be a function because we forced this section to pass the horizontal line test. And if it passes the horizontal line test, then the inverse is a function. But what's going to be the domain and the range? Well, what did we say was that line that a function and its inverse or mirror images over? Yeah?
Y is equal to X.
Y is equal to X. So what that basically means is when you change something into its inverse, Y is equal to the X, and X is equal to the Y. The Y's and the X's switch places when you change something into an inverse. So let's think about domain and range. Domain represents which letter? Your X's or your Y's? Those are your X's. And what about your range? Yeah?
Your Y.
Those are your Y's. And we just said that if you know something about the original, you switch the X's and the Y's to figure out the inverse. So what do you think is going to happen to the domain and the range here when we talk about inverse sign? Yep. They're going to switch. So here, notice it says domain, negative pi over 2 to pi over 2, range, negative 1 to 1. Well, when we talk about inverse sign, the domain is negative 1 to 1. And the range is negative pi over 2 to pi over 2. So as long as you know some facts about original sign, you also know the facts about inverse sign. You just have to switch all the facts. And I'm going to draw a picture of inverse sign, just like I did squaring and square rooting, so you can see what it looks like. I think this is a little harder for people to kind of visualize what the reflection would look like. So there's, before I get rid of it, there's squaring and square rooting. Now let's do sine and inverse sine. Okay, so we're going to put in sine x and inverse sine x. Now I need to set my window. Okay, I want to look at a window that's going to fit this inverse trig function. So let's set our window to this. Let's set domain negative 1 to 1. And I know the graph is going to be right on the edge of the screen, but it's okay. And let's do the range negative pi over 2 to pi over 2. Now, if I'm using pi over 2 and negative pi over 2, I'll get it. What units are pi over 2 and negative pi over 2? Yep. Those are radians. So I need to make sure that my calculator is in radians. If you want to do it in degrees, fine. But then use negative 90 to 90. Don't use negative pi over 2 to pi over 2. So let's put it in radians. Let's draw them both, and then I'll put in the line y equals x, and we can see if they look like reflections of each other. Okay, so there's the section of sine we're looking at that passes the horizontal line test. And what you're looking at in red is inverse sine. And if you draw in the line y equals x, I think it's a little harder for people to see it, but they are mirror images of each other if you flip them over that line. Remember what's going to happen to sine, like right here. This is the top of the wave. So you want to think about it, the top of the wave is perfectly flat. Kind of, it flattens out. Well, if the sine function is flattening out, then the inverse sine function is verticaling out. However you want to think of it. They're doing the opposite. I just didn't draw quite enough for you to see it get horizontal right in there. But that's sine and inverse sine. Okay, so what's in red is the graph of inverse sine, and it does not go beyond the edges of those dots. That's the entire picture right there. It stops. So any question on where those domain and range come from? All right, let's look at cosine. So think about the graph of cosine. Let's put that in. And the hope is that the graph of cosine is going to pass the horizontal line test. If it doesn't, we need to find a section that does. So here's the graph of cosine. Does cosine pass the horizontal line test? Okay, Caleb?
No, it doesn't.
No, it fails it. So what does it mean for something to fail the horizontal line test? It means that the function we are looking at does not have an inverse. Okay, the function we are looking at does not have an inverse because it fails the horizontal line test. Well, we need to make it pass the test. All right, so let's make a box. It's going to be 2 tick marks wide. That's always how wide you make it. Just try to draw it the best I can. Each tick mark again represents 90 degrees, and I want to find a section that passes the horizontal line test. How about that section right there? Does it pass there? No. No. All right, well, let's try negative 90 to 90, because that's what we did before. All right, there's negative 90 to 90. How's that? No. All right, well, let's keep going. How about right there? Yeah, that section's perfect. So that section starts at 0. And each tick mark is 90, so where do you think that one ends? It ends at 180. Yeah. Or 0 to pi. So in order for inverse cosine to exist, that's what we're going to have to do. We're going to limit our regular function to that. Let's write down what that is a little more formally. So this is for the original cosine. That's the graph you're looking at right there. Domain, we're going to limit it 0 to pi. And what's the range if you look inside that box? Yeah?
1 to negative, or negative 1 to 1.
Yep, negative 1 to 1. Yeah. It's the same range as sine. Now, these are for original cosine. What's going to happen to the domain and range when we talk about the inverse? They're going to switch. So your domain is going to be negative 1 to 1. There you go. Domain for inverse cosine, negative 1 to 1. And the range is going to be 0 to pi. Because here, the domain was 0 to pi. So they just switch places. Now, inverse sine and inverse cosine, they both look like waves. When we talk about inverse tangent, that one's a little different. Does anybody remember what the graph of tangent has that sine and cosine doesn't? Yeah?
It has the asymptote.
It has asymptotes. What kind of asymptotes?
Horizontal.
What does somebody else think? Are those horizontal asymptotes or vertical? Yeah? Yeah, those are vertical because you can tell if you draw a vertical line in like this. As the blue curve goes up and down, it's getting closer and closer to those vertical lines, but it's never touching. All right, look at that. Does that graph pass the horizontal line test? No. It definitely fails it. Because it fails it, that means this graph would not have an inverse we can work with. So what are we going to do? We're going to limit what we look at, and we're going to find a section that does. Let's draw a box 2 units wide. And we're just going to try what we did the first time. That's negative 90 to 90. Does that section pass the horizontal line test? Yep.
Yeah.
Yes. But what do we know is happening at negative 90 and 90? I drew them, but I just erased them. Yeah?
There's vertical asymptotes.
There's vertical asymptotes. All right. So, yeah, we just said that there are vertical asymptotes. So what that means is we are going to limit it from negative 90 to 90. But because there's asymptotes at negative 90 and 90, you can't include negative 90 and 90. So it's going to be very similar to what we did for inverse sine, except you're not going to have a bracket here, you're going to have a parenthesis. It cannot equal negative 90 or 90 because of the asymptotes. Okay?
Is the inverse tangent just coefficient?
No, that's the reciprocal, which is different. Yeah. I'll talk more about that in a second. All right, so here, this is for tangent. Again, it's the original. Domain, we're going to limit negative pi over 2 to pi over 2. But make sure you put a parenthesis because there are horizontal asymptotes, vertical asymptotes. And what about the range? How high and low? Yeah?
Could be negative infinity to infinity.
Yeah, it's all real numbers. The graph of tangent goes up and down forever. Alright, so there's 2 facts about the original tangent. Now we talk about inverse. What's going to happen to the domain and range when we talk about the inverse? Yeah, they're going to switch. And remind me, what kind of asymptotes do we have in that picture again? Yeah? Vertical. So what do you think happens in inverse tangent? We're going to have asymptotes.
Horizontal.
But they're going to be horizontal. Yeah? And so instead of having a vertical at negative pi over 2 and pi over 2, we're going to have a horizontal at negative pi over 2 and pi over 2. And I'll show you what the graph of this one looks like in a second. Okay. So with regular tangent, the range was all real numbers. With inverse tangent, the domain is all real numbers. And the domain for tangent was negative pi over 2 to pi over 2. That becomes the range for inverse tangent. And keep in mind that the 2 vertical asymptotes we had at negative pi over 2 and pi over 2 are going to turn into horizontals. That's what happens when you reflect something over the line y equals x. Anything vertical turns to horizontal. Anything horizontal turns to vertical. Right, let's look at a picture of inverse tangent. Alright, so I'm going to set my window back to negative pi over 2. which is about 1.57. So you know what? I'm just going to type it in that way. 157. And for the y min and max, well, wait, did I type that in right? No. Sorry. Domain is all real numbers. So for domain, that's your x's. You can set that as big as you want. Probably -10 to 10 is enough. It's the range that you want -pi/2 to pi/2. So that's your y's. So -1.57, 1.57. So it looks kind of like regular tangent, but it's on its side. And this top and bottom piece just keep going forever. And the graph is always going to be stuck between those two horizontal asymptotes, just like it was stuck between the verticals in regular tangent. Any questions on, I'll make that so you can actually see the domain and range again. Any questions on the inverse tangent? Yeah?
Do you have to like set the window like that in order to find it, or can you just look up the graph?
So you need to set it somewhat accurately, or you might not see it. Because, especially with inverse sine and cosine, they start and they stop at certain points. If you don't set your window to the right thing, you may look at the completely wrong spot and see a blank screen. With inverse tangent, you probably wouldn't see a blank screen only because the domain is all real numbers. So since this graph goes left and right forever, you're probably going to see something because it's so big. But inverse sine and inverse cosine are really pretty small pictures. Very, very small. In fact, I can show you that just by, if I do inverse sine x. If I do zoom 7 and I do inverse sine x, you can see that's the entire picture. It's pretty small. And if you zoom out a little bit from that picture, now you really can't even see it because it's such a small graph. So you really need to set your window to zoom in enough to be able to see it. All right, so we just talked about sine and inverse sine, and the symbol for them, which I've been writing down, I should probably mention a little bit, has to do with this trig function with a -1 up a little bit higher. When you write a trig function with a -1 in that spot, it means inverse trig. So, you have your trig function here. And then in that spot right there, if you put a -1, it means inverse. Now, what's a little weird is if you put, and it's not an exponent. When you put a -1 there, it's just a special symbol that means inverse. But if you put a number here that's not a -1, it is an exponent. So if you did something like this, let's say you put a 2 in that spot, that does mean this. It does mean to raise tangent to the second power. But when you put a -1 there, it does not mean to raise it to the -1 power. It's like a special case. But that's why I can see when people put a -1 here, most people know, oh, when you raise something to the -1 power, it means to flip it. Which is why you might think like tangent and cotangent are inverses. But when you put a -1 here, this has nothing to do with flipping anything at all. So that's why the -1 can be a little confusing. Okay, so it's just a special symbol that means inverse, and your calculator uses the same symbol. If you press second and then a trig function, you'll see it puts a -1 above the sine function. All right, so the whole idea of inverse trig is that it cancels out regular trig. Why would we cancel out regular trig? Let's say you had an equation like that, and I ask you to solve for x. You need to get rid of sine. And the only way to get rid of sine is to take the inverse sine, and then it would cancel out regular sine. So if you took the inverse sine of everything that's on the left, and you took the inverse sine of everything that's on the right, what happens on the left is this. Inverse sine and regular sine cancel each other out. And you're left with something you could type in on your calculator and get the answer. So that's where inverse sine comes up. When you want to cancel out regular sine and solve for a variable that's right there. Now, it works both ways. You can have the inverse on the outside and the regular on the inside, and they cancel. Or sometimes they might be switched, depends on the question they give you. So the idea in formulas 1a and 1b is that if you take the inverse sine of the sine, or you switch that, and take the sine of the inverse sine, the answer that you get is exactly what you started with. So let's try it on the go. And I'll do it in degrees just so I can show it to you with a nicer number. Let's take the inverse sine of the sine of, and somebody give me an angle. Yeah? 45. So based on typing that in, it says inverse sine and regular sine are going to cancel each other out. And the answer I get is whatever I typed in. So what do you think I'm going to get when I get enter here? Yeah?
45.
Yeah, and I get 45. And thank you for saying 45, because there are certain angles that would not have worked. But 45 is one of them. That does work. Okay, here's another one. You could type in, 84. And sine and inverse sine cancel each other out, and I get back whatever I started with. But this only works if you pick an angle that's between the original two numbers that we said it had to be. When we started the whole thing, we said we had to find a section that passed the horizontal line test. That's the section that passed. So we still have to stick with those numbers. Watch what happens if you plug in a number that's not between negative 90 and 90 into Formula 1a. Somebody give me a number that's not between negative 90 and 90. Yeah.
302.
302?
Yeah, that works.
Oh, okay. Got it. 302. Well, I definitely did not get back the same answer I typed. There's a pattern to the answer you get back. We're not really worried about that pattern right now. But the point is, it didn't work. So, Formula 1b, same idea. If you take the sine of the inverse sine, you will get back the same answer you typed in, if you are between certain numbers. The numbers you have to be between, you can figure it out by looking at the inside function. And you ask yourself, what is the domain? So think about inverse sine. And you can look back in your notes. What did we say for inverse sine, the domain is? Yes?
Isn't it the negative 1 and 1?
It's negative 1 to 1. Yep. So let's try something that works. The sine of the inverse sine of 0.24. That's definitely between negative 1 and 1. When I hit enter, based on that formula, what should I get? 0.24. And I do. Let's try something that's not between negative 1 and 1. Let's just make it 1.24. This time, when you try to do it, you don't even get a different answer back than you started with. It just says that the number you tried to type in is not in the domain. You can't even do it. Okay? So this formula will only work between negative 1 and 1. Okay, and I'm not going to keep typing them in on the calculator, but it's the same idea for cosines and for tangents. Yep.
So is this like to check your answer? Like when you get the answer and then you use this to like check your answer? Or is this like finding the answer?
So we're going to use this to find an answer when we talk about solving trig equations.
Okay.
We're going to have to use inverse trig to get the variable by itself. So this is going to come up more in chapter 7. We're not really doing a lot with it today in terms of like solving a problem. I'm kind of just telling you what the formulas are.
Yeah.
But we'll do more with them later on. Okay, so inverse cosine and regular cosine cancel each other out. That's the whole point I want you to learn from today. They cancel each other out. And you get back what you started with. But what is the domain of cosine? And you might think, well, it's a wave. It goes on forever. Yes, but we limited it. We had to limit it to make this whole lesson work. And it's not negative 90 to 90. Yeah?
It's 0 to 180.
0 to 180. So 0 to 180 in degrees, or 0 to pi in radians. And where you're really going to see this come up a lot is when we start talking about more with triangles and trying to solve for angles. And the nice thing is when you're dealing with a triangle, you know that all your angles have to be less than 1. Yep. The angles have to be less than 180, but they also have to be more than what? Yep.
0.
Have to be more than 0. Well, that's exactly when this formula works. This formula works if you're trying to find an angle that's between 0 and 180, and that's exactly what happens in a triangle. So this formula is perfect for dealing with triangles. Okay, and let's look at this one. Cosine of the inverse cosine. Those two functions cancel each other out. And the answer that you get back is what you typed in. But what is the domain of inverse cosine? It's very limited what kind of numbers you can plug into inverse cosine. Yep. It's negative 1 to 1. Yep. And this is the formula where if you try to plug something in that's bigger than 1, it's going to give you an error. It's not even going to work and give you a different answer. All right. And let's look at the tangents. Okay, so again, what's the big idea? Inverse tangent and regular tangent cancel each other out. And you get back the answer you started with. Now, think of tangent. When I drew that box on the screen and I moved it to find a section that passed the horizontal line test, what did we decide on for a domain for tangent? From this number to this number. It's kind of like sine, but we got to be a little careful, yeah?
Wait, for the domain, was the domain for that one negative infinity to infinity, or was that the range?
Yeah, you're mixing up. That's for regular tangent. The domain is how far left and right the curve went. Yep.
That 90?
It always has to be 180 wide. 0 to 90 is kind of part of it. Yeah.
It's negative 90 to 90.
Negative 90 to 90. So is it exactly the same as this one?
No.
No, it's a little different. What's different about this negative 90 to 90?
Oh, no, never mind. Nope. I was saying.
You can't include the 90s.
You cannot include the 90s. That's why there's no equal twos under them. Why can't we include them? What was on the graph, negative 90 and 90? Yeah? Asymptotes. You cannot hit those asymptotes. Think of them like an electric fence. You can't touch them, right? So we can. Bad things happen. So negative 90 to 90 can't include them. And now, switching. When you switch it, it's just like an order of operations thing. It's just which one you do first. So now we're doing the tangent of the inverse tangent. So think about the one that's inside the parentheses and ask yourself, what is the domain of inverse tangent? And if you can't remember it or you forget it, remember, the domain of inverse is the same as the range of the original. So you can think of either one. It's the same thing, they're just switched. Yeah.
Negative or all real numbers.
Yeah. So that's negative infinity to infinity or all real numbers. Yep. So all 6 of these formulas are based off of the domains and the ranges that I gave you right there for inverse cosine and inverse tangent. And right there for inverse sine. So any questions on those formulas? Yes?
Why did you put the arrows in?
Oh, the arrows, I'm just pointing to the one to focus on to figure out this restriction.
Okay.
Yeah. So when I want to figure out what this is, in my head I say, okay, look at the middle one, and I ask myself, what's the domain? All right, so once we know the originals, we can transform the domain and the range, just like every other function we've studied all year. But this doesn't, you can't figure this out unless you know the originals to start with. And that's what I already gave you for inverse sine, inverse cosine, and inverse tangent. All right, so we've done this at least 6 or 7 times, but we can quickly just go through what each letter there does. Does anybody remember when you add or subtract inside the parentheses? What does that do to your graph? We're talking about either shifting, stretching, one of those two.
It shifts it left or right.
Yep.
If it adds, it shifts it left, and if it subtracts, it shifts it right.
Yes. Yep. So A is your horizontal shift. What about B? It's still inside the parentheses, so it has something in common with A, but then it has something that's different. Yep.
B can either horizontally stretch or shrink.
Yep. So it's stretch or shrink, and again, it's the opposite of what you would think. The bigger you make B, the more it shrinks. The smaller you make B, like 1/3 or 1/4, the more it stretches. And what if B was a negative?
If it was negative, it would flip.
Yep, if B is negative, that causes a horizontal flip. Right, now let's look at the ones that are outside the parentheses. So C is kind of like B, it's multiplication, but it's outside instead of inside. Yep. So it's going to be a stretch, but it's vertical. And the idea here is it's what you would expect. The bigger you make C, the bigger stretch you get. The smaller you make C, the more you shrink it. And if C is negative, what would happen with that? Yep.
It would vertically flip.
Yep, it's a vertical flip. The last one is D. And we're doing them in the order you process them in when you do a problem. A, B, C, and then D. What's D? So it's adding, like A, or it could be subtracting, but it's outside instead of inside. Yep, that's your vertical shift. Okay, so what we're going to be doing, let me just show you kind of like a problem. There's a problem. It's an inverse trig function, and I want you to find the new domain and range based on that transformation. So, how do you do it? To find the new domain, we're basically going to set up something like this. We know that the original function had a domain. Say it was like, I don't know, -1 to 1. We're going to put the original domain, the lower one on the left, and the higher one on the right, like -1 to 1. And then in the middle, we're going to put the argument in the middle. So like in that problem I showed you a second ago, I think it was 1/3 x. So you're going to be setting up an inequality, and then you're going to solve for x. So if it was a 1/3 x in the middle, then I would say multiply everything by 3. Multiply the left by 3, the middle by 3, and the right by 3. And then you'll have x alone in the middle, and then there's your answer. So you're going to put the original domain on the left and the right, put the argument in the middle, and then solve. So that's how I think about doing the domain, and we'll go through one. And range, I don't really do anything like super or mathematical or set up a formula to do that one. To figure out the new range, all I do is take into account if there was any stretching and then any shifting in that order. Let me show you an example with kind of simple numbers. Let's say you had a range that went -1 to 1. And you stretched that by a factor of 3. So stretch by 3. If it went -1 to 1, and you stretched it 3 times as much, what would it be? Yeah?
-3 to 3.
It would now be -3 to 3. That's how I figure out a stretch. You just multiply the values you had by the stretch. If you stretch by a half, well then it would shrink. Now, let's say you took that and you shift up 1. This is why it's important you know what each number does. So you'd have to say, okay, now I have a shift up 1. Can anyone tell me if you took -3 to 3 and shifted that up 1, what would be your new low value and high value if they each go up 1? Yep.
-3 to 4, or -3, 4 if you shift it up.
Well, think of it, it's all shifting together, right? You're not leaving one where it is and moving the other one.
But yeah, so it'd be
They move
-2
together.
to 4.
Yeah, -3 to 3 would be -2 to 4. That's all I do to figure out the range. Figure out if there was a stretch and then a shift. And that's just an example. Let's try this one. Inverse sine 2x. First of all, how many transformations are in this problem? Like if you look at this one, If there's a number for the A, B, C, and D, then you have 4. How about this? Yeah?
Only one.
Only 1. So that means either the domain or the range is staying the same because you're only doing one thing to it. This is taking the place of B in our formula up above. What does B do?
Horizontal stretch.
That's a horizontal stretch or compression. If you stretch and compress things horizontally, what does that change? Does that change domain or does that change range? The domain. That means this 2 has no effect on the range. We can look up our notes, look at the inverse sign, look up the range, and just write down what I gave you for range, because that's not changing. What is my range for inverse sine? If you can't remember it, if you're like me and you forget it sometimes, okay, I don't remember the range of inverse, then I'll think of the domain of the original, because they just switch places. Yep.
Negative pi over 2 and over 2.
Yep. So that's great, because that's the ones with pi, so we don't have to work with those. And now to find the new domain, we're going to set up an inequality. It says put the argument in the middle. That's the argument, 2x. And then put the original domain on the left and on the right. What's the original domain of inverse sine? Yeah?
8 pi over 2 and wait.
No, that we already used that.
Oh, okay, so that's just negative 1.
That's negative 1 to 1. And now we need to solve for x to get our new domain and range. How would we get rid of the 2?
Divide 2 by everything.
And look what happened to the range instead of being our domain. Instead of being negative 1 to 1, now it's negative a half to a half. This 2 caused it to compress, which is exactly what should happen. The bigger you make this number, the more it shrinks. And the domain shrunk by a factor of 2. So if they ask you for your answer as an inequality, you could write it just like that. What about if they ask it like we wrote the range? What would you put? Yeah?
The bracket negative 1 half, comma, 1 half.
Okay. There's your domain. Yeah.
Oh, sorry, where'd you get the negative 1?
That comes from the original domain from that tape, the 3 that I gave you when we started out. So we had those 3 formulas, domain and range, for inverse sine, inverse cosine, and inverse tangent. So we just have to look those up. All right, let's try this one. Well, it's the same type of problem. I'm plugging in a value for b. So I know the range is staying the same. We already know the range from the last problem. Okay, to find the new domain, start with the original. What's going to go in the middle? Yep. 1/3 x. Fill in your inequalities. And now solve for x. How would you get rid of the 1/3 here? Yeah.
Multiply by 3.
Multiply everything by 3. So what is my new domain after I do that transformation? Yep.
Negative 3 to 3.
Negative 3 to 3. Any question on that? I think I have another one with inverse sine. Let's try something different. Let's do inverse cosine. Okay. Little different. What's the plus 2 doing?
Vertical shift up.
It's going to shift it up. When you shift something up, what does that affect? Domain or range? Yeah?
Your range.
That's going to affect the range. So we're going to have to figure out the range. But that means we know domain stays the same. So look back at the chart I gave you for inverse cosine. What is the domain of inverse cosine?
-1 to 1.
Yes, -1 to 1. All right, now the range is going to be shifted up 2. So first, let's write down the original range. What does inverse cosine normally go between? It's not the -pi/2 to pi/2. You're thinking inverse sine if you do that.
0 to pi.
That's 0 to pi. And how are we shifting that range? It was 0 to pi. Yep.
Up by 2.
Up by 2. So my new range is going to be, just do a +2 on each of those. So instead of going 0 to pi, it's going to go 2 to pi +2. There's no reason you have to write that as a decimal. If you want to put 5.17, you could. But I'm just going to leave it as pi +2. So because of that, some of these answers come out a little messy sometimes. Any question on that? All right, let's try this one just because it's a transformation we haven't done yet. It's multiplying by a number in front. And then I want to do the last thing with you, which is on the calculator. Okay, what's that 5 doing? You're multiplying by a 5 in front. So it's taking the place of the C in the example. Yeah,
The vertical stretch.
that's a vertical stretch. What does stretching vertically change? Domain or range? Changes the range. I'm going to stretch it taller. Domain stays the same. Inverse cosine. What's my domain?
-1, 1.
Same as the last problem. -1 to 1. Okay, range. Well, we also wrote that down. It's 0 to pi. But you're going to take each of those values and they're going to be multiplied by 5 times as much. So what's my new range going to be? Yep.
0 to pi.
0 to 5 pi. Only reason that one stayed the same is because it was 0. When you multiply it by 5, it's still 0. That's a bracket. Any question on finding domain and range? Okay, so last thing with transformation. On this one, I want you to just tell me what the transformations are. You don't have to tell me domain and range. Just identify the transformations. First thing I usually do is make sure that that equation is written just like this. And you can go through it very easily. That problem is not written like what I have. Does anybody see what I would need to do first to make that look like what's on the other page?
You need to multiply 1/4 by x and 1/4 by b.
Yeah. So we should have inside the parentheses 1/4 x plus 2. Now identify your A, B, C, and D, and just tell me what each one of them do. And make sure it's in that order. Start with it.
So for first you would shift it left by 2.
Okay, so yep, that's the first thing. Shift left 2. Okay, what's the second thing? Yep.
Horizontal stretch by 1/4.
So let's think about what's going to happen there. Is that 1/4? I agree, it's horizontal. Is it going to stretch it or compress it?
Press.
It's a small number. Yeah?
So it's gonna stretch.
It's going to stretch it. Remember, small numbers make it bigger. When it's inside the parentheses, everything's backwards. So there's 2 ways you can say it. You can either say stretch by a factor of 4, because it's really going to stretch it 4 times as big. Or you could say compress by 1/4, but that's using a double negative. That's like if I wanted to say shift up and I said shift down -2. It's kind of weird. I mean, if you shift down negative, it's really up. But it's easier to say it in a positive way than say a double negative. So I would just say stretch by a factor of 4. That's what that 1/4 is. Horizontal stretch. Factor of 4. Okay, what about the 3? Yeah.
It would be a vertical compression by a factor of 3. Or
Careful, that's not the opposite anymore, because now we're outside.
So then it would just be vertical stretch by a factor of 3.
Right, so yeah, we gotta be careful with that. So once you get outside the parentheses, it's not backwards. Positive is up, negative is down, things are normal, no more bizarre. Alright, so vertical stretch by a factor of 3. And what about the -5? Yep. Right, normal. Negative is down. Shift down 5. So that's how you identify the transformations. All right, and the last thing on the calculator. So I've kind of been showing you how to do these a little bit, but I want to make sure everyone understands the buttons to press. To do inverse trig on the calculator, you press second, and then you press the trig function you want to use. We are only focusing on inverse sine, cosine, and tangent right now, because those are what you have buttons for. So let's do A together, and then I'll ask somebody how to do B. Well, the first thing is to read the directions and look at what units they want you to use. If they don't specify, let's just go with degrees. It doesn't say. So I'm going to put my calculator in degrees and then just type in second sine of 0.5. That is 30 degrees. When you do inverse trig, you are solving for an angle. So make sure you label it correctly. If it's degrees, you need the little circle. And does anybody remember what that's the same as in radians? 30 degrees? Yep. That's pi over 6. Always, always, always do it in degrees first. Because if you did that problem in radians, you're going to get an answer like this. I don't think anyone in here is going to recognize that 0.52359877 is pi over 6. But it is. If I actually can type it in. It is pi over 6. The calculator won't tell you it's pi over 6. You're not going to recognize it. So how would you get that? Do it in degrees first all the time. Then, if you need to put it in radians, fine, do it off to the side. Multiply by pi and divide by 180 to change it to radians, but do it yourself by hand. And then reduce it. 30 goes in once. 30 goes into 186 times. pi over 6. Let's try the next one. Inverse cosine of negative 0.7. What do I press to type that in? Yep.
You do second, and then press cosine, and then type in negative 0.7.
Okay, I am going to put it back in degrees because I said to you we were going to do degrees for these problems. Now, that's not a nice answer. It's not like the last one. Because it didn't come out nice, technically it doesn't matter if I do it in degrees or radians, because I'm not going to be able to give you a nice answer no matter which way I do it. Okay, but I said stick with degrees for now. So 134.43. Okay. How about inverse tangent of 4.3? How would I type that in? Lucas?
Second
Yep.
tangent and
4.3. And you get 76.91. Again, not a nice answer, so if you don't get a nice answer in degrees, you're not getting a nice answer in radians. Now, inverse sine of 1.2. I got an error. What does the domain of the inverse sine have to be between? And this number is not.
Negative 1, 1.
You have to plug in a number negative 1 to 1. You can't do that. This has no solution. Right, so that's the first part on inverse trig. Now, one thing, I don't remember if the book uses this notation or not, but there is an older way of writing inverse trig functions. I think it's before they really use this negative 1 as a symbol for it. So if you see arc sine anywhere in the book, it's the same as the notation that I gave you. I use what's on the left because that's more modern. That's what your calculator uses. But not as many books use that. But if you see it, it means the same thing. Same for inverse cosine. Same for inverse tangent. It's just an older way of writing. But let's stick with the more modern way.
The odd applies to 1 through 9, right?
Yeah, 1 through 9 odd, and then 13 to 20, 22 to 24, and 27 to 32.